Welcome to your Unit 2 review for geometry. This unit regarded transformations, rigid motions, and congruence. The idea of this unit was again that rigid motions, whether it's a rotation, a reflection, or translation, will always produce a congruent image. Part 1 was the 14 multiple choice problems, and in this review I'm covering the 12 free response problems. You will need your compass and a straight edge to handle several of these problems. This video is somewhat long at about 58 minutes because there's so much explanation involved. If you don't understand things, of course, fast forward or rewind or repeat the parts that were most confusing to you. I would suspect that it might be the constructions and how to find rotations and whatnot. So let's begin. We have a triangle here, and we're told that we should use this mapping rule to draw its image on the grid. When it says show how you obtain your answer, what it means is that you should show what's going on with the coordinates. So we have this coordinate here, which is at 6 and 1. We have the coordinate up top here because this is the origin, by the way. So this one here is at 1 and 8. And the third one over here is at -2 and 1. So to show what I'm doing with my mapping rule, I'm going to lay out the original coordinates here and show that how they map. And so by applying this movement on the x-axis, every x coordinate is going to move to the right 5 places. And applying this rule here, which says basically whatever the y value was of the coordinate, make it the negative. Our new coordinates are going to be at 3 and -1. 6 and 1 will then move over to 11 and -1. And this one here moves +5, so 5 added onto that position now gives us 6. And when we get the negative of the y value, we get that. So I'm going to now graph these coordinates. And our new image will now be at 3 and -1, 11 and -1, and 6 and -8. Which puts the new image here. Okay, are these two figures congruent? Absolutely. They're congruent because what we've done here is a translation and a reflection. Right? This image is translated to the right 5 places, and then it flipped over the x-axis. So it moved here and then flipped over upside down. So yes, the two triangles are congruent because you can map the first one onto the second one. By translating it 5 units to the right, and then reflecting it. In or over the x-axis, I'd rather say over. These are rigid body motions, which means nothing has changed shape, right? Nothing's expanded or contracted. These are rigid body motions. and all rigid body motions must be congruent. Okay. Problem number 16. I'm going to move the paper up. Okay, so 16, you have a triangle shown there in your picture with those coordinates. You have to draw now, I see primes, so I have to draw a new image of this triangle after a 90-degree counterclockwise rotation about the origin and give the coordinates of this. So what that means is you're going to do this a 90-degree, each quadrant is basically a quarter turn, right? 90, 180, 270, 360, right? 4 quarter turns brings you back to start. And we're moving counterclockwise, which means the direction is going this way as opposed to clockwise. As I've probably shown you in class, the way I like to do that is physically take my paper and move it a quarter turn counterclockwise. And then I imagine what those new coordinates are. So right now, this thing here, this image, if we number our quadrants here, this would be, you know, the lower right quadrant is what? Quadrant 4, right? This is 1, 2. Am I doing that right? I'll come back to that. This over here. I'm going to move it counterclockwise, a quarter turn. So let me turn my paper around. I'm doing this for people who are having a hard time. And I'm noticing, sorry, that was quadrant 2. It's now up here. If I reimagine this is X, I'm just imagining, and this is Y, then I can pick up my new coordinates just by reimagining that. So what I mean to say is, it looks like A is at 2 and 3. A prime, and I'm going to write it on the side, goes to 2 and 3. And B, when I do the rotation, now it's going to be called B prime, seems to be at 1, 2, 3, 4, 5, 6, and 3. And C is at 2 and 9, C prime. And so what I did was I don't like memorizing rules. I like to see what's happening. Now I'm going to turn the paper back. I've written down where I believe the coordinates should go to, and I'm going to write it here. So I have to show my work here. So I had first A was at 3 and -2. And when I do the 90-degree counterclockwise rotation, let me refer to my notes here, I see that I planned it to be at 2 and 3. B was originally at 3 and -6. But when I did my rotation with my paper, I found B to end up at 6 and 3. And C, which is originally at 9 and -2, moves to C prime, which is now at 2 and 9. Okay, so I'm going to graph this right now so you can see what I'm talking about. Okay, and I'm going to use my red marker so you can see it. So A prime will be at 2 and 3. That's going to be A prime. B is going to be at 6 and 3. B prime, 6 and 3. I like to label them, it helps me. And C prime was at 2 and 9, which puts it here. Okay. So this is the second figure that I just mapped here. And again, look at it. Turn this paper and think for a moment. Hold this in your mind, right? It's a right triangle. The hypotenuse is on the right. The short leg is on the bottom. And let me bring it back this way to make sure it's right. And I'm noticing, yep, that's what I have going on here. Short leg, long leg. I'm a little sloppy here, but that's the way it is. Oh, I messed up on B prime. 6 should have been here. Sorry. Disregard that. Okay? Part B. If this new figure, A prime, B prime, B prime, is mapped again using a translation such that its vertices end up here, tell what happened to move it there. Give a rule for this translation. So let me pick up a different color so again you can see what I'm doing. I'm going to use blue. And let me map these new coordinates. So A prime, double prime, is at -3, 1, 2, 3, -4, right there. Did I do that correctly? Yeah. B prime, double prime, goes to 1 and -4. That brings it 1, -4. A double prime, B double prime, and C double prime is at -3 too. Here it is. So what this question is saying to you is, if you map this triangle, the one right here I have in red, take this triangle and somehow move it and bring it over here, what is it exactly that you would do to make that happen? Okay? And what you might notice is the triangle has the same orientation. It's still facing upward there. The hypotenuse is still on the right. It didn't turn around or anything. It simply slid over to the right and then slid down into place. So that motion here, well, the answer is, what is the rule for this translation? A prime, B prime, C prime triangle ends up moving, let's see, 1, 2, 3, 4, 5 places to the right, left, sorry, move 5 places left, units left. And once it moved left, it then moved down, right? Here's the A prime. It went 5 this direction, and then it went down 1, 2, 3, 4, 5, 6, 7 positions downward. Okay? Let's go on. Next problem is 17. Okay. So problem 17 talks about constructing the image of this triangle after it's been rotated 180 degrees about C, using only a compass and a straight edge, and leave all your marks. What this means is you have to really understand what a 180 rotation seems to look like. So right now, notice the orientation of this. DF, the long side to me, I guess, or, it's down on the bottom. And if I turn this paper twice to accommodate 180 degrees, whether I go right or left, 2 quarter turns will be the same thing as a point rotation. So I'm going to do 1 turn and a second turn. And I see that the image now is going to look like with the hypotenuse piece on the lower left. So let me bring the paper back on here. What's happening here is that when we do 180 rotation, every point is going to go from, for instance, the left side of this point of rotation, it's going to go all the way along a straight line, collinear, to the right side. So what you need to know, or like F here, look here where it is from C, and we just have to jump it over to the other side. And D here, if you look at this from C, I'm sort of putting little dots here, just continue it, and it ends up on the other side here. Well, how far on the other side does it go? This is where your compass comes in. Measure it. So my point is on C. Here's my D mark from C to D. So if I flip my compass, I didn't even lift it off the paper, and bring it to the other side, I'm going to put a mark there. And now I'm going to pick up a ruler or a straight edge, anything that'll do that. We're not measuring, we're just using it for the straight line effect. I'm going to connect from D. It has to go through C, and however long this line is here, it's going to go to the other side, the equal length, which I've just marked with that compass mark. This piece is the same length as this piece. And so let's do the same with the other ones. Again, take my compass. I'm going to set mine at E because that's the point it has to reflect over. And I'm going to tighten it up so I can set the pencil on F and get that value, that measurement. And here's my mark. Right. So that's how far it is. And I'm just going to leave the point, flip it to the other side, and draw an arc. Again, all 3 points have to be collinear, so I'm going to notice my pen's down first, or my pencil's first. Line it up with point C, bring it to the other side till I hit the arc. There's my second one, so that's going to be F prime. By the way, this one is D prime, and E has to come to the other side over here. And so again, we're using the compass to be a measurement tool. Point, pencil, show the mark. That's the length. Flip it to the other side. And make your straight line. Pencil down. Connect it to the midpoint there, which is C. Bring it to the other side. Here it is. So now I just need to connect these 3 points, and you will see that I have the identical triangle, but it's been rotated 180 degrees to the other side. Let me label this as E prime. And so this blue one there, if you can concentrate on just that, you don't have to color it in, I'm doing that so you can see, is the same as that one. As you can see, even when I turn my paper upside down, I have the 2 same images. Because by turning my paper upside down, I've done 180 degree rotation. Okay? So the logic is when you rotate about 180 degrees around any particular point, each original point is simply going to flip to the other side, the same distance. For number 18, again, we're constructing. This one's easy. It's a basic construction. How do you do a perpendicular bisector? So to bisect this line, we need to know where the middle is. And one construction will solve both problems. So first of all, I'm going to put my point on G and open my compass beyond the halfway mark. Right, there's the halfway mark. I'm going to open a little bigger than that. My compass is set, and I'm using the twirly thing at the top, and my pressure is on my needle here. And I'm just letting that compass draw a real light line. I don't need it ground into the paper. I have not changed the compass, same setting. Make sure I lock it in on my other point. And again, draw. So what I've done is created 2 arcs that are each the same distance from their opposing endpoints. I have 2 intersections. Connect them. And by default, not only have I divided the line segment into 2 equal pieces, I have also made right angles. Each angle here is 90 degrees. Number 19. If G was reflected, referring to this picture, if G was reflected over the line you constructed in problem 18, would it land on H? Well, absolutely. Yes. Since the line bisects GH, and bisect means to cut in half or cut into two equal positions, line segment GH, and is perpendicular, I'm using symbols, to it, then by definition, of a line reflection, G will map to H when reflected across the line. Putting it all together, you should be able to answer number 20. What rotation would be used to map G onto H? How would you rotate to get G ending up here? In other words, how would you turn your paper? Would a quarter turn do it? Remember, H was to the right. No. Would a quarter turn do it? Yeah. Initially, G was on the left and H was on the right. And I've just reversed it. Not to mention, originally, when I had the paper, notice the left side of the picture is higher up than the right side. If I go back to the original thing, it was the same thing. The left side was higher up than the right side. So I had to turn the paper twice to get it there. So a rotation of G clockwise or counterclockwise about this point here, like that's my point of rotation. You could lock it down, spin your paper, and there I just turned it upside down. See, it's still there. So a rotation of, I left off the word G, clockwise or counterclockwise, either direction, about point D, I'll call that D, B, by an angle of 180 degrees, will map it to G. Well, we'll map H to G, right? H to G and G to H. Because all 3 points are collinear, right? They're all in the same line. And the measure of GD there is the same thing as the measure of HD, which I labeled there, right? Because we bisected it. Number 21. Another compass sort of problem. We have to draw a reflection, a line of reflection. Well, this is coming off of the previous problem because it's building on that idea that when something reflects over a line, that line that connects the 2 points is the midpoint. So, in the diagram we have triangle DEF, and it is the image of this triangle. In other words, this was the first thing, and then it was reflected over some line that I can't see. You could literally take the paper, fold it in half, and hold it up to the light. You see my triangle through the paper? If you can see that, you could do that. Give you an idea, right? Now I have the two triangles lying on top of each other pretty much, and I'm making that fold line, and look what I've done. There's my line of reflection. But I have to do this with a compass. So the idea again is, first of all, understand that B is going to map to E if I fold over that line. So what I'm going to do is draw lightly, ideally with a pencil line there, and I want to find the middle. I want to bisect it. So I go back to my compass because the distance from the line of reflection should be the same on both sides. So here's my compass. I guess I'll put it on E because right now it's easier for me. Use what you can. Open my compass so it marks out to beyond the halfway point. I kind of went big. I don't have to go that large. There's the fold. So my compass is set larger. And I'm going to just draw an arc like before when I did a perpendicular bisector. See, the perpendicular bisector construction is perfect for any time you need to find the middle of something. So there I go. And now I've confirmed that if I connect this point to this point, that is the perpendicular bisector. And so all I need to do is connect it. That's my line of reflection. Okay. Number 22. Here's a quadrilateral, and they're telling us some things. Always use that to mark your picture with stuff that you know. That's kind of my rule of thumb. Whether I need it or not, I mark everything I understand. So I know that AD is congruent to BD. So I'm going to make a mark here. AD, that's my symbol, is the same thing as BD. Right there, I don't even read the rest because I'm already understanding that this is, if I turn it, I see an isosceles triangle. And if this side is the same as this, I already know these two angles are the base angles, and they're congruent as well. So let me come back and continue marking what I know. Measure of angle ADB is 30. Well, that's right here. And BC, this line here, is perpendicular to both here, this line, as well as to this line. So I'm marking that. Those are 90-degree symbols, right angles. 90 degrees. The whole one. So we have to use this information and figure out what the measure of angle DBC is. Pick up another color. DBC is this one. That's my X. Alrighty, so let me think about this. Alright, I know that angle A, the measure up here, this angle, is the same as this one here because base angles in isosceles triangles are congruent. This angle here in yellow has to be the same as this one here. So I'm going to concentrate right now on this triangle here. And I know that a triangle always totals 180 degrees. So what I'm thinking here is, let me use a color you can see. The measure of angle A is the same thing as the measure of angle ABD. Right? This one is equal to this one. And this whole thing is a triangle. I know triangle ABD is 180 degrees. I already know this piece is 30. So I'm going to subtract it. By eliminating that, I now know what these two together must equal. That leaves me with 150 degrees to divide equally. So I'm going to divide in half, and I find that A is 75 degrees, and this one here, ABD, is 75 degrees. Okay, but I have to get this angle. Thank goodness I wrote this symbol here because I don't have to read again. I know that this is a total of 90 degrees right here. This part of it is 75. So the measure of angle DBC equals 90 minus 75, which means it equals 15 degrees. And that's my final answer, and I'm going to write it here. Getting towards the end of this now, number 23. Okay, in the following diagram, triangle ABC, this one, has been transformed into this one, A double prime, B double prime, C double prime. How did it get from here to here? Give one such sequence of transformations that would map this one to this one. So there are a few possibilities. I'm gonna first, let me see, what am I thinking about? Well, first of all, I notice this one seems to be upside down in relation to this. So I'm thinking there is some sort of a reflection that's going to take this triangle and flip it upside down. That's one way of going about it. I'm going to use my marker so you could see what I'm talking about. So if I flip this upside down, right here on the line, B and C will stay there. Let me let's imagine this is the line of symmetry. And A is 4 above that line, so I'm going to bring A prime 4 below that line. So now I have this. See how I made a mirror image? Except this one is not that. So what I've done first is I reflected over the line x equals -3. And now I need to slide it over here to the left. And it looks like I have to slide it down one time. So this is my way of doing it. You might say other things. So my answer is if triangle ABC is reflected first over the line x equals -3, and then I'm going to slide it to the left and down. So that's a translation. Translated to the left, I have to move 1, 2, from B. 1, 2, 3, 4, 5, 6, 7 places left. 7 units left. And then I have to bring it down so it's aligned. 1 unit down. Triangle A double prime B double prime C double prime is produced. Now, you may have done it differently. Maybe you first said translate it 7 units left and 7 units up, and then reflect it over the x-axis. You might have done that. I just saw this more directly. And so this is why geometry is challenging. A lot of it has to do with your perception or perspective. Don't think because someone does something differently, it's necessarily incorrect. Why does this sequence prove the two triangles are congruent? We haven't changed any of the dimensions of these triangles. We've simply reoriented them in space. And again, it comes down to the idea that both translations and rigid motion and reflections are rigid body motions. which preserve the shape and size of the object. See, things are congruent so long as you don't change their size or their shape. Once you start expanding things and blowing them up, we have a whole nother kind of transformation going on. Okay? Up to problem 24. Again, I like marking my pictures as I read along. So, AE, this line here, AE and BD bisect each other at C. Well, to bisect means to cut in half. And that happens at your midpoint. So I understand that if this is cutting this one in half, this is the midpoint, and this piece must have the same value as this one in measurement. And conversely, if this one is cutting this one in half, this one being cut in half, here's your midpoint, and this piece must be the same as this piece. Give a rigid motion that would map triangle ABC onto this one, and explain why this shows the two triangles are congruent. Well, first of all, hopefully you get it. We're doing take your paper, if you turn it 2 times, 1 and 2, we have an identical image. And that's a rotation of 180 degrees, which we've done already. So, to answer this, if we rotate triangle ABC, by 180 degrees around that turning point, that around point C, point rotation, then it will map to triangle EDC, the other one. This will map onto here, because B will land on D and A will land on E. B will end up here and A will end up there. Due to the two segments bisecting each other. Since rotations are rigid body motions, they don't change size or shape. Of the original triangle. So they must be congruent. So the two triangles in diagram A prime B prime, that line segment there. It is the image of this one after this one has been rotated about some unknown point. So how do we get this to turn and end up over here? Again, I like to visualize this. So I'm going to take my paper, and I'm keeping in mind right now that AB is like to the right side of my paper and A is higher than B. So I'm going to do a quarter turn to the left. That's not it. A is not higher than B, right? Or vice versa. But if I do a second quarter turn, doesn't this appear to be what I started with when I had the paper in the right position? 2 quarter turns of this orientation brings it here to here. This is a rotation of 180 degrees. The question is, over what point do I have to lock my pen down to do the spin? So that it ends up in the exact same orientation. Okay. So draw in segment B prime B. Let's do that first. And if you recall, point rotations always revolved around a point directly in between the midpoint between the before and after motions. If I connect B with B prime and find its middle point, and I do the same for A and A prime, and find its midpoint, which is somewhere here, and I connect them. Let's see what happens. Picking up my compass. First, let me physically locate the middle between B and B prime. I just sort of sketched a guess right now, so here I set my compass. There's an arc. Come to the other side, set my arc, and I'm going to connect them. So I just drew a perpendicular bisector there, but that's not what our goal was. I'm going to do the same for this line segment that connected A to A prime. So I need to adjust my compass to make sure it's wider than the halfway mark. I'll go a little bigger. And I'm going to draw my arc. One there. Again, I'm trying to get the perpendicular bisector so I can get the midpoints. Right, that's the midpoint. That's the midpoint there. That's congruent to that. This one here is congruent to this one here. But where do these two meet? They're meeting out here. I'm going to call this C. And so, to find the center of rotation, I have to find that common point where these two revolved about. And that would be right here. And if you want to play with that idea, you have a piece of somewhat transparent paper. Let me see if I have a piece somewhere. Tried to show you. Let's see if this is transparent enough. I don't know. I can see it. I don't know if you could see it. I'll sketch over it. So here's the original A, B. See? Something there. And here's the other one. Paper's a little small. B prime. A prime's just off the edge. Look at this AB line. Here's where I think C is. Right there. Okay. If I lock that point down, let's see if I turn this paper 2 quarter turns, in other words upside down, will this end up where that other line is. So here's a quarter turn. I think 1/4 turn did it right there. See? Can you see? Wow. So this is my point of reflection, right? The center of rotation, so now I'm writing my answers. The center of rotation must be equidistant from each of the images, right? From B and B prime, as well as from A and A prime. By the definition of rotation. To rotate something means you're just turning it around a point of rotation, and everything has to still be the same distance from the point, no matter where I rotate it to. So the center of rotation must lie on the perpendicular bisector of that line we created here, B, B prime, that line segment. So part C, I kind of went ahead and did the whole thing. Complete the construction to locate the center of rotation and label it as C and leave all construction marks. Well, I've done that. I left all my construction marks, my arcs here showing how I found the perpendicular, the bisector of each of the segments, and I found that common spot where both bisectors meet. Since the center of rotation must lie on this line of the two perpendicular bisectors, we're going to have that intersection of C. And so there's nothing really in words to write here except to be sure to show everything you've got going on there. And there it is. So again, here was my original image, and if I was going to rotate it, wherever it rotates to, in this case, B is going to rotate to B prime, I have to find that bisecting line, because it's always going to flip or go to the opposite side of the line of bisecting. Over here, A and A prime, again, A ended up going here. How did it flip over to the other side like that, or rotate there? We find the bisector. Where the two bisectors meet, which we labeled C, that now is your physical point in space that you can lock down and spin your paper around if you need to see what's happening. And now we are up to the very last problem. This is a more challenging one. All right, given the regular pentagon, and by saying regular pentagon, I understand two things. It has 5 sides, and by saying the word regular, all sides and angles are congruent. If a line of symmetry is drawn right through from point B, right, cutting this image in half, literally in half, fold your paper if you want to. Explain why it must be the perpendicular bisector. So understand, the line of symmetry has to go directly through, something like that, right? So that this will map to here and E will map to D, and now hopefully we understand that when we reflect something over a line, that line has to be the midpoint here. so that everything flips an equal distance to the opposite side. Okay? If a line of symmetry for this was drawn through B, explain why it must be a perpendicular bisector to side DE. And here's my answer in words. A symmetry maps a figure I think my pen is dying. Maps a figure onto itself. If a line of symmetry passes through B, then it must pass through segment DE right here. When ABCD is reflected across line BF, reflected across line BF, notice my notations here, line, right? Line. It's not a line segment, it's a line. E must map to D. E must map to D, and D must map to E. Right? This one should map over to there. That one should flip over to this side. For this to happen, BF must be line, must be the perpendicular bisector. Of segment DE. What is the minimal angle to make this happen? To map B onto A, you'd need a minimum rotation of 72 degrees. In other words, think about this. To revolve completely around and get back to start, if I were to take this image here and A is on the top and I turn it, turn it, turn it, keep turning it, turning it, turning it, turning it, still turning it, A is not on the top, keep going, da la 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 la. Okay, A is on the top. To go around, that's a 360-degree turn. But the question here is, how many degrees do I physically have to turn it to get over to here? Not a whole 360. So the way to do this is to map B onto A. Realize that we have 360 degrees to go full circle, but I only have 5 positions on this object. So what is 360 for every fifth of that turn? So I divide by 5. And so that's a 72-degree rotation to get from one position to the next. So from here to here is 72. I'm off. From A to B is 72 degrees. If I turn again, that's another 72 degrees. If I want to bring A full round to D, that's 3 turns to the right clockwise. So that would be 3 times 72. So the question says, how many degrees do you have to turn to get B over to E? And it says minimum. The reason is because if I turn my image to the right clockwise, I'd have to turn 1 to 2. I'd have to do 3 turns to bring B over to E. But if I go counterclockwise, 1, 2, right? That going this way, that's 72-degree turn and another 72-degree turn. So the minimum I would need if I'm being efficient would be 2 times 72 degrees, which is 144 degrees, would be the minimum rotation. Explain why 180 degrees rotation around point F in either direction would not lead to symmetry. Again, an 180 degrees rotation is basically taking your paper, let's say, and turning it upside down. And now I have this, which clearly was not what we started with in the first place, because now I have a flat edge at the top. Whereas when I started, this pentagon had the point at the top. Okay, so only rotations that are integer multiples of 72 for this one. Of 72 degrees. For every 72 degree turn will I have symmetry. Since 180 is not a multiple of 72, it will not be a symmetry. And the final question here. Construct a line of symmetry that passes through point A. Leave all construction marks. So if I'm going to go back to my picture, I'm going to slide my paper. And I fully understand, this is a question to really test your understanding, that the line of symmetry that would divide this image nicely in half so that all points are equidistant from the line of symmetry, and that's the key idea. A line of symmetry is the position where all points can reflect to the other side and match to another point there. So I have to construct this. All points have to be equidistant from either side. So in order to do that, I'm going to pick up my compass. And I want to find the midpoint of this side. I can see visually my line is off. I was sketching. So let me find the midpoint. Again, making a midpoint or a perpendicular bisector. There's one curve. Don't change it. Come to the other point. Make the other curve. Much better than my sketch. So if I connect this to this here, I will have the midpoint. And notice how it goes right on up and matches with A. Right? This piece is the same as this one. This is now my line of symmetry. And I don't know, I could call that, since F is here, if I want to call that G, AG is my line of symmetry. Sorry. And there you have it. So that's the end of your Unit 2 review. Watch it over and over again if you need to. I find that by doing things multiple times, it's a lot easier to remember what I have to remember. And good luck on your test.